Okay, so just a quick reminder of where we are. Everything's on Canvas. I have put some of the lectures that we've done in there already in reverse order, or more recent at the top. So the parametric curve stuff, the both calculus and just definition, and then the conic section. So already in just a few days, we've done about a week and a half worth of stuff during a normal semester. So if it feels like a lot, it is. Um, but today we're gonna, zoom ahead. We're gonna do 9.4, and then hints at 9.5, and then that's chapter 9, which is what the test on Monday is on. So we're just gonna fly through. Today we're gonna do maybe the first half on lecture, and if you have questions along the way, as usual, just hop in. If my screen freezes again, which seems to be the way of the world, uh, we'll just, let me know and I'll try to reset it. And then the second half, after break or something, we can do lots of problems because 9, 2, and 3 are due at 1 o'clock. So we'll just put off the questions until then, but keep them in mind as we go. So, all right, well, we're just going to hop right in. So this is 9.4, and so this is on polar graphs, polar coordinates. And you probably have seen some of this stuff before, basic radar. If you're looking at a radar blip, the little bar going around in movies or something like that. Maybe in surveying, you might have done some of this stuff. You can check with Reister on that. And so basically the idea is when you draw, that's terrible. Let me turn this sideways here. When you draw a set of axes, you're automatically imposing this XY structure on it. And at some point, someone picked, you go over first and you go up and you hit a point and you call it XY. And not really sure there's any reason why you couldn't have said, well, let's go up and over and let's call it YX. There's nothing strange about that. We just picked it, and that's the convention. So if I want to get to this point, and I'm here, well, I could go over and I could go up. Maybe if I'm driving in a city in a car, they call this the taxi cab metric, where you have to follow the road. So you go from here, you go over, and you go up. But if you're standing out in the middle of a field, I don't think that's probably the way you're going to go. You're like, well, I want to go from here and I want to go there. So that's exactly what I'm going to do, is I'm just going to go straight to it. That seems to be the shortest path, so let's follow the shortest path. So they call this, the distance, sometimes it's D, but it'll be related to circles eventually. So we would call that distance there R. So right off the bat, we know the distance between two points is a straight line. So, we just get the distance R. But anytime we do this, it hopefully, like, wait, we went over it up and now we're going straight there. Well, that looks like a triangle. So right off the bat, we get the relationship from a Pythagorean theorem that if I did x squared plus y squared, I would have to get r squared. And so, yeah, that's just from Pythagoras. Thank you for that. But if you also just told someone, hey, just walk 10 feet, they would say, yeah, but in which direction? So that's the second part for polar coordinates, is you give the direction. And there's a couple ways to do this, but we also just decided to pick, well, let's start on the x-axis and let's rotate a certain angle. And along the way, this angle has become theta, Greek letter theta. Again, just for convention. Nothing special about it. It's funny, when I showed this to my colleague at UVA, who's a biochemist, he's like, what? You put the angle here? Have you ever seen a compass? And so, if you ever seen a compass, where is the 0 degree? It's not to the right, it's to the top. So this is one of these things that automatically are like, you guys are crazy in the math field. You just pick anything you want. We're like, let's put the angle over here. All right, well, so x-axis is like the 0 degree angle, and then this is 90 degrees up here. But anyway, so when we do that, we also get a relationship between theta and x and y. So see, if you look at, talking about trigonometry in here. If you were going to do a triangle, and maybe I can just go ahead and drop a perpendicular down here. This is y, this is x. So the trig function that relates all of this, you could use sine and cosine, but I want to just leave out r for a second and look at just x and y, that if you take the tangent of the angle, you get opposite over adjacent, so y over x. So right off the bat, you get this relationship, which we're going to use quite a lot, between r. How do you, if you knew r, or if you knew x and y, you could get r. If you knew x and y, you could get theta. So that's the relationship between these two things. Again, there's no numbers on the screen, so let's do a couple of examples with numbers. If I had the point 1, 1, and again, I should probably be careful here. If I write x, y equals 1, 1. So I'm just talking about, I go x, I go y, I go 1 unit over, and I go 1 unit up, and that's the point 1, 1. But if I wanted to write this in terms of polar, well, then instead of going over and up, I go straight towards it. So I have to know what that distance is, and then I have to know what the angle of rotation. I don't know if that looks simple, but just try and be a little careful on this. The radius of this, well, if I go over 1 and I go up 1, well, I could use Pythagorean theorem. This would be 1 squared, so that'll be 2. So I would have r squared equals 2, so r is square root of 2. So the distance along that diagonal line is square root 2. The angle is, well, now I got to be a little careful because angles are not always unique. If I rotate here, you probably can see that that's 45 degrees. But we're not going to use degrees. You know, so just take your calculator and put it in radian mode from now on, at least in math classes. So the angle there is 45 degrees, which is pi over 4 radians. So that those two numbers there would describe that point. And just for shorthand, we would write it in this order, r and then theta. So we would write r theta equals square root 2 and pi over 4. And we have to just be careful, you know, make sure that when we write a coordinate like that, we have to tell whether it's polar or it's xy, which is called Cartesian or rectangular. It looks like a rectangle. But it's also not unique, because what I could do is I could take my angle and I could go 45 degrees, and then I could go 90, 180, 270, 360, and then I could add another 45 onto that. So now I'm at 405 degrees, and I'm still rotated around the same amount. So I could just rotate all the way around and get back to that, which would be 9 pi over 4. And if I did that, rotate all the way around, I'd still walk square root of 2 units out. And so that is a second representation of the exact same point. So these things are definitely not unique. I could wrap around twice, I could wrap around 3 times, or I could just go back the other direction. And I could write, let's see, r is also square root 2, but if I wrapped around backwards, I would go negative pi over 4, 2 pi over 4, 3, 4, 5, 6, 7. I could go negative 7 pi over 4. And all of those things will get me to this point right here, 1, 1. And not only that, it's even worse. What I could do is I could think about, you're looking at this point. You want to look at this point. But if you rotate it around to here, then what angle is that? I would go negative pi over 4, negative 2 pi over 4, negative 3 pi over 4. And that is, you're facing the wrong way. Because if you're looking out and you just rotate your body around to here, you're looking to the southwest. But what you could do is you could then just take a step backwards. So if you walk backwards, it's maybe not too surprising that I could do this. I could say negative square root 2. So these things not only have values, they have directions as well. So kind of like a vector. So any of those coordinates, and I can add 2 pi to any of this sort of stuff, or 4 pi or 6 pi, or I can do negative. All of these things will give me this. So it is, the point of that is it is definitely not a unique setup in Polar, which can cause some problems. But we'll just have to be careful.
So I have a question.
Yeah.
So you just knew because of the pi circle the angle, correct?
Yes.
Well, when I put in 1/1 inverse tangent, I got 45. Is that the same? That's pretty much the same thing.
Right. So the the relationship between radians and degrees is that 180 is pi.
Okay.
So 90 degrees would be pi over 2. So keep in
Okay.
mind. So 45 degrees would be pi over 4.
Oh, yes, sir. Thank you.
Yeah. And again, when you put this in your calculator, does it give pi over 4? Or does it give an actual like number? Oh, it gives 45.
Yes, sir. It gives me 45.
So if you change your calculator into radian mode, so you go like in mode, and then I think just, I can't remember what the actual, let's see. So
It just says radian. I got it.
Yeah. Angle. You can change it from degree to radians.
Oh, okay.
Yeah. And your calculator won't necessarily show pi unless you have it like in exact mode. But if it's not an exact mode, it will show, 3.1415, however many decimal places you ask it to show.
Yes, sir.
Pi over 2, 1.57, whatever. So pi over 4 is going to be around half of that. So I think 707 is a number that you'll start to see. So, yeah, so good question on that. We're going to try to avoid that because we're going to want to actually sometimes calculate with these by plugging them in, and we don't want to plug in 45. It won't make any sense. So anyway, we have that. If I wanted to go backwards, I could just convert that. If I said that my angle, so if my r theta was, let's say the radius is 5 and the angle is pi over 3, and we want to go back the other direction. Well, when we do this in Polar, we actually we don't know what x and y are, so we just draw the theta axis where theta equals 0 here, and then if you've ever seen Polar plot paper, it has like dotted lines that are in concentric circles going out. It's like graph paper for x and y. You've got all these little squares. Well, this one has circles because I'm going in circles out. So this one says to rotate pi over 3. So you convert that in your head, that's 60 degrees. So I would rotate 60 degrees. So that's sort of roughly there, pi over 3. And I just follow it out. 1, 2, 3, 4, 5 units. And so if that distance there is 5, then that would be the point 5 units out at a radius or a rotation of 60 degrees. So how do you convert that back into x and y? And the answer is to use a triangle. So if I just came in here and went triangle, this is 5. I drop one straight down to get 90 degrees. And this is pi over 3. Then the x coordinate will be whatever the distance is on the bottom. The y coordinate will be whatever the distance is up and down. And so you've got to go back and look at trig. I know that if you took the sine of pi over 3, you get y over 5. So there's your so. Sine is opposite over adjacent. And the cosine of your angle pi over 3 is x over 5. So that's your ka, right? Adjacent over hypotenuse. And so if you just multiply both sides by 5, you'll get that y is 5 times the sine of pi over 3, and x is 5 times the cosine of pi over 3. And now you got to go back and say, okay, what were those again? Let's see, 60 degrees, the cosine is a half. So that tells me that x is 5 times a half, and y is 5. Let's see, the sine of 60 degrees, you go back and try to remember in your brain, That's a square root of 3 over 2. So this famous triangle of a half, square root of 3 over 2, and 1 for 60, 30, 60, 90. Rears its ugly head again, so can't escape it. So the xy coordinate would be 5 halves, and then 5 square root 3 over 2. So that would tell you how far over to go and how far up to go. And that's unique, right? If you go over and you go up, boom, you're done. There's no other way to get there. You can't wrap around. You can't go to the end and come back. You could reverse it, I guess, and say go up and over, but the convention is X and Y. So in general, go the other direction. I have my thing slanted here. I probably shouldn't do that. We get that the X coordinate is always whatever the radius is times the cosine of whatever the angle is. And y is r times sine. So if you knew r and theta, you could use the formulas on the previous page. If you know, if you knew x and y, you could get r and theta. If you knew r and theta, this gets you back to x and y. So just do the basic truth. And sometimes if the angle is not very nice, you're gonna start getting bad values in here, and you might have to do approximations. Leave it as arc sine or arc cosine, and in your head or in the calculator, you can just work it out to say, make yourself feel a little bit better. Now, here's the fun part. Instead of doing points, we can do entire curves. And so just looking at entire curves, both in polar and in rectangular. So here's what I mean. If I did x squared plus y squared equals 1. So we've already done this in the first section on conic sections. We know that that is a circle. So if I do the axis here, I get a circle. And if I want to convert this into polar, then I got to go back and I got to look at my formulas and just go back. I knew these relationships here between x and y. If I knew x and y, I could get r. And if I knew x and y, I could get theta. So you look at this and wow, I've already got x squared plus y squared. So x squared plus y squared equals 1. So if I convert it over here to polar, I can just use the fact that x squared plus y squared equals 1. Or equals r squared. That's my formula. So I just plug in r squared. So I get r squared equals 1. And then I can simplify that. R is technically either 1 or minus 1, but this is a simple setup that the equation of a circle that's centered at the origin is just that. R equals 1. I don't know what theta is, so the assumption is that theta wraps all the way around. So I can get the entire thing. But just writing r equals 1 means take every single point that's 1 unit out. Well, that's a circle. So that's pretty cool that polar works really well with circles. That's what we do. And so that converts the entire curve into just a very simple equation. If I wanted to go back the other direction, I could say something like theta equals pi over 4. And that's a polar curve. And, well, which polar curve is that? If I don't list what r is, then the assumption is just like before with theta. I'm assuming that I'm talking about every single r. There's no relationship for r, so I just select all possible r's. So here's what I mean. Again, I'm going to draw theta equals 0, just the polar axis, and not x and y yet. Theta equals 4, I rotate 45 degrees. Didn't write 45, pi over 4 degrees. And then I pick every single r along that angle. So I'm going to pick, this is r equals 0, r equals 1, r equals 2, r equals 3. And then back the other direction, r equals -1, r equals -2. And I do all of them. So if I put them all together, and draw a straight line, then that is the equation of a line. It looks weird, but it is the polar equation of a line. Now, if you convert that to rectangular, what line is that? Well, in terms of X and Y, so rectangular, I think you probably don't have to do too much thought here, is that that's just the line Y equals X. Just looking at it. So that's just by inspection here. Now, if you really wanted to say, well, how did you know that for sure? Well, you got to go back to the relationship that, what was it? It was the tangent of the angle is y over x. So if I use this relationship, I plug in theta equals pi over 4. Well, the tangent of pi over 4 is equal to 1. So I get 1 equals y over x. And if I multiply both sides by x, I'll get x equals y or y equals x. So that's exactly the line that I'm talking about. So there's ways to go from these strange equations in x and y to polar, or from polar equations back to rectangular. So there's your basic ones. Now they start to get a little funky. So let's try this. So for example, y equals 1 plus cosine theta. Not y, r. R equals 1 plus cosine theta. So this is a function. I'm going to do this for all angles, theta here, 0, theta, 2 pi. And so what I've done is I've really written as r as a function of theta. So just like normally it's y is a function of x, I'm going to do r as a function of theta. And now how do you plot any graph in rectangular is you just plot points. So we're going to do that, where I'm going to pick a theta, find the r, and then plot the coordinate. And then just do that over and over and over and over until I've got enough that I can just connect up the line. So now you're like, oh, I got to do a lot of trig, but not too bad. It's just cosine. So here we go. Let's just start. So at 0, I get 1 plus the cosine of 0, which is 2. So cosine of 0 is 1. So 1 plus 1 is 2. So if I try to plot that point, and I need my polar axis here, that's when theta is 0. Well, when theta is 0, I go out 2 units. And I just plot a point. So that right there is the point 2, 0 in polar. R is 2, theta is 0. 0 to 0. So that's my starting point. This is the origin. I don't know if I'm going to have the origin or not. I just probably shouldn't put a college out there, but let's see what happens. Okay, well, let's plot the ending point, 2 pi. And then we'll fill in values in between, just like we kind of do normally. So if I plug in 2 pi into my function, I get 1 plus cosine of 2 pi. And the cosine of 2 pi is also equal to 1. So the cosine of 360 degrees, that's 1 plus 1, I get 2. And now where is 2 pi? Well, I start here and I rotate around. 2 pi is 360 degrees. So I go 90, 180, 270, 360, and then I go 2 units out. Well, guess what? Boom, I'm right back to where I started. So that's also the point to 2 pi. We already shouldn't be too surprised because every time I wrap around 360 degrees, it's the same as if I stayed at 0. So let's fill in the points in between. So say 180 degrees. So my picture, I'm going to rotate around to 180 degrees. I'm looking to the left. How far out do I go? That's what radius means. So I'll get 1 plus cosine of pi. And now you go back and say cosine of 180 degrees or cosine of pi. That's -1. So I'll have 1 plus -1 or 1 minus 1, which is 0. Which means I don't go out any units. Or again is how far you go out. So I rotate 180 degrees and I don't go out any units. So I'm right there. That's the point where R is 0 and the angle is pi. So if that's all you know, it's like I start here, I have to somehow get over to here, and then somehow I have to get back to here. So that looks, all right, fair enough. That's a little strange, but let's see what happens. Pick some points in the middle. So 0 and 180, let's just pick a point in the middle at 90. So I'll have 1 plus cosine of pi over 2. Cosine of 90 degrees, that's 0. So I'll get 1 plus 0, so that's 1. So that means I rotate 90 degrees and I go 1 unit out. So I rotate to 90 degrees, which is straight up, and I go 1 unit out. Right there. So that's the point where R is 1 and the angle is pi over 2. So now let's follow that up. I got to go from here to there, and then back to there. And probably not going to be a triangle, but I only have 3 points, so that's all I can do so far. So we're just going to put in a bunch more points if you're following, and we'll do a couple more examples if it's still kind of a mystery, but we'll see. So let's do 270 degrees. So I rotate 90, 180, 270 down here. How far do I go out south? So I do 1 plus the cosine of 3 minus 2. And that cosine of 270 degrees is also 0. So I'll get 1 plus 0, and that's also equal to 1. So I'll go 90, 180, 270. I'm looking down, and I'll go 1 unit out. And 1, 2, 5, 2. Okay. So follow up. Start there, go up there, go down there, go down there, go back. This is just a big triangle. Well, that's, I don't know. Cosine is kind of a mystery sometimes. So let's try something else. Let's try something at 45 degrees. How far do I go out for 45 degrees? Let's see if I can put it in here. 45 degrees, I get 1 plus cosine of 45 degrees, or pi over 4. And that value is square root 2 over 2. So I get 1 plus square root 2 over 2. So cosine is, so if I approximate that, it's around 1.71 units out. So I rotate 45 degrees, and along that 45 degree line, I go out 1.7 units. So if you need to, you can sort of do this. You know this is 1 unit, so it's about 1 unit is about right there. So I go 2 units is about right there. So I don't quite go as far, maybe about right there. So 1, 2 might be there, so I just go 1.7 units out. So that's 1.71 at 45 degrees. Now, it's not a triangle. I'll go from here to there, to there, to there, to there, and then back to there somehow. Now, I think in order to really see this, we need one more, and then we can sort of maybe connect the dots. Let's go 45, but over here, so northwest. So that's 1, 2, 3 pi over 4. 3 45 degree angles. So I'll get 1 plus cosine of 3 pi over 4. And cosine of 3 pi over 4. Well, that should be square root 2 over 2, but in this second quadrant, cosine is negative. So this is actually 1 minus square root 2 over 2. And so if I work that out, it's around 0.3. That's an approximation. So I rotate, this thing's going to be in the way. I'm going to just move it here. I want to rotate this way over to what angle that is, 135. 135, I want to go out, but only go out 0.3 units, maybe about 1 unit. So I go out 0.3 at 135 degrees. So I have to go from here to there, to there, to there, to there, and then there, and then there. If I were to plot a lot more points, maybe not too surprising on the symmetry, I get a point that's directly opposite this, and this one is directly opposite this. By symmetry, I could plug in negative pi over 4, negative 3 pi over 4, and it gets similar values. So I don't know if your eye is doing it or not, but I want to go from here to there, to there, to there, to there. Yeah, almost did it. It's supposed to be nice and symmetrical top to bottom. I could do it again, but I'm not going to. So let's make this dot bigger. So that shape is like dimpled. It's not a circle. Keep it a little bit. This one, I don't know if it looks like it, on the side, it looks like a heart. It looks like maybe other things, but it's, or a peach or something like that. So we have to give it a fancy name, right? Because this is scientific. So this graph here is something called a cardioid. So cardio, for heart, and this is an example of a basic what's called cardioid plot. I'm not going to tell you what the equation for x and y is just yet because it's ugly. But trying to come up with an XY equation that gives that, just like we did on the previous ones, it's hard to turn that into X's and Y's. We're going to do some of them, but not this particular one. All right, so we've done that. Let's just try one more, and then we'll take a break, and then and do just a couple more. But we'll do a basic one here. What about this? R equals cosine of theta just by itself. Yeah. Theta goes from 0 to 2, just like we did before. So the radius is determined by some function that has theta. So I'm just going to plot points again. I know what I'm doing. I get too carried away sometimes. I don't want X and Y because I don't know what they are. I want to plug in theta and get on it. So 0, let's put some points in here. 0, pi over 4, pi over 2, pi, and then let's see, maybe there will be some symmetry that goes on with this. Let's see. So if I plug in 0 into the cosine function, that's equal to 1. So cosine of 0 is 1. Cosine of pi over 4 is square root of 2 over 2. We just did that one. Cosine of pi over 2 is equal to 0. Cosine of pi is negative 1. So a little fast there, but these are some of the basic values for cosine. So if I want, now I have a negative value, so just gotta be careful on how that gets plotted. So let's see. I know that the largest this can get is 1 because that's the bound on cosine. Cosine only goes between -1 and 1. So I can make this over here equal to 1. So at 0 degrees, that's here, I go 1 unit out. And I just plot the thing. So that's the first one. 0, 1, 2, 2. 1, 2, 4, 2. Next point, I go 45 degrees. So there's theta equals 45. I go square root of 2 over 2 units, which is again around 0.707 or 0.7 or 0.71. Can't really draw it. Anyway, so 1 unit out is about there. So I just go maybe about there. So 45 degrees, I go out 0.7 units. At 90 degrees, so straight up, I go out no units at all. So I would stop there. So that's the point where R is 0 and theta is pi over 2. Theta or, sorry, R theta. Now, here's the tricky one. Pi -1, that means I'm facing right, but I rotate my body around, so now I'm facing left, but I take 1 step back. So instead of going out with the plus, with the minus, you go 1 step back. So boom, you actually hit right there. So that's when R is -1 and theta is pi. So somehow I got to go from there to there to there to there. But again, I don't think it's probably a triangle because cosine doesn't, it's not so straight. So I need to actually put in a few more values. I don't think I have room, but maybe I'll just put them down there. So pi over 6, so 30 degrees. cosine of 30 degrees is square root 3/2. So that is around 1.73 divided by 2. So that's around 0.86-ish. Again, we're not going to have this super accuracy on the graph, but I go 30 degrees, which is roughly there, over 6, and I go 0.86 units out. It's not quite 1, maybe 1 is about right there. I'm going to do just one more and then fill in by symmetry. 30, 60, 90 is a nice one, so it's 60 degrees. So it's 60 degrees is sort of about right there. It is power of 3 or 60 degrees. The cosine is a half, so 0.5. So I go out 0.5 units. Maybe about right there. And that's R is a half, and the angle is 60. Now, again, I'm supposed to go from here to here to here to here to there and then over to there. So you may not be too surprised that if you plugged in negative pi over 6, negative pi over 4, negative pi over 3, you get exactly the mirror image of these points down below. And if I had drawn this perfectly to scale, turns out that what I did is a circle. Now, the center of this circle, if you think about it, if this is the diameter of the circle, then this is at 0 units and that's at 1 unit. The center should be right there at half, 1 unit, half unit out, and you don't go up at all. So if I wrote this, and how far is the radius then? I go out, it would be 1/2. So if I wrote this in rectangular coordinates, just using section 9.1, let's go back to section 9.1 here. That should be, let's see, x minus 1/2 squared plus y minus 0 squared equals 1/2 squared. So it's x minus the x coordinate of the center, y minus the y coordinate of the center, and then the radius squared. So that looks like it should be the same as this, because they both give the same picture. This just happens to be the polar way to give this picture. That's the rectangular way to give this picture. But we're going to take a quick break, and then I'll show you how to convert back and forth without having to draw anything on that. So quick break, and be back in just maybe 8:15. We'll see you then.